All right, welcome everybody to week 11, day 2. I don't know, lost track. So we're gonna do a little maze thing here. So copy main.cc to old main.cc, then main.cc. So I'm just going to keep most of this here. Code this from scratch. I'm going to keep my. I'm not going to redo the input and things like that because that's kind of a waste of time. All right, so create a 10 by 10 array. Okay. Clear start, clear end. Sure the array is solvable. Okay.
Can you stream?
Yeah, I can do that too. Okay, so what I'm gonna do is basically system clear is fine. Okay. 1, 1, 2, 2, 3, 3. Input starting location 0, 0, 4, 4. Okay. So that's the input phase. We kind of don't need to go over that. So you got here. So what's the interesting thing is the solution, right? So what we want is a recursive. We want a recursive solution to this because we're talking about recursion right now. The solution I have in there right now is not recursive. I'm just gonna make this global. Oops, what happened here? Yeah. Oh, it should work. Okay, so I've got a function to print the array, clear the array. That I am going to delete. And what I'm going to do is create a recursive function bool. I'm going to create a function called solve maze, and it's just going to take in a row and a column. That's it. So that's the thing. The rest of the stuff here is all just window dressing. It prints out the map and all that stuff. It's not really that important. So let's see what we got here. Place the walls on the map. Put the start, end, and then what we're going to do is cout bool alpha, and then we will bool solvable equals solve maze, passing in the starting and ending locations. Might need to make these a global as well. Just to cut down on the number of parameters that we have here. Okay. Empty wall player. And I'm gonna create a thing called crumb or something. And so, like, every time I move to a spot on the maze, I'm going to drop a breadcrumb there, just so that if I ever come back there again, I'm like, oh, I've been here before, and I can return. Okay. All right. So let's do this. Input the goal location, bool alpha, bool solve maze, and then we're going to pass in the starting, let's say, player X and player Y. Okay. Player X and player Y. Actually, we don't even need to set the goal X and goal Y, do we? Okay. Because we're gonna mark that spot with a goal there. Okay. And player X, player Y. Okay, so everything I've done so far is just the standard like user interface, like enter a goal, enter the maze. You know, there's nothing interesting about what I've done so far. What's interesting is this function here, solve maze. Okay, so we're going to do a recursive maze solving algorithm. Okay, so we're going to pass in the start location, and then it's going to recurse out from there. And yeah, and then it'll return true if the maze is solvable. It'll return false if the maze is not solvable, and that's it. So we got solve maze. Let's put this up here so I can look at the different options. Okay, so if we're supposed to solve the maze and the current spot we're passed in is not, if it's a wall or if it's something like that, then we just return false. Okay, so so first of all, we should check to see if we hit the exit, right? So if my array and the row, actually we first need a bounds check, right? So if row is less than 0 or column is less than 0, or row is greater than or equal to max size, or column is greater than or equal to max size, then we return false. Okay, because obviously you can't solve the maze by going outside of the maze. You can use a 2D vector, yeah. It's just a 2D array that I'm using, it doesn't matter. Okay, so if we go out of bounds, always do that. Always bounds check before you do a square bracket. Okay, so if my array row call equals goal, then I have successfully solved the maze, and I can return true. If the spot that we are at is actually, let's just pull this out. Let's make this variable as a char. Char spot is equal to my array row call. I have to keep typing this damn thing over and over again now. So if the spot is the goal, we have successfully solved the maze. If the spot is a wall, or if the spot is a crumb, or if the spot is starting location, player, or yeah, that's good. Then we return false. So the only remainder here is What are you complaining about? Non-void, I know. The only remaining thing to do is we are on a new open spot we have not visited before. Okay. So basically, this is all the base conditions, right? That stop it from infinitely recursing and things like that. So if we hit the goal, we found it a thing. If we hit a wall, we didn't find a thing. If we got a bounds, we didn't find a route. Okay. I moved the map in global space just so I don't have to keep passing it to the function over and over again, you know? Okay. So now we're on a new spot we've not visited before. So here comes the recursive step. So we have to mark our spot. So my array row call is equal to crumb. So we're going to mark the spot as having been here before. And now we're going to recurse. So we're going to recurse north, south, east, and west. And if either of those routes returns true, if any of those 4 routes returns true, then we return true. Okay, so we will now return solve maze row -1 call, or solve maze row +1 call, or solve maze row call -1, or solve maze row call +1. And that's it. Yeah, that should do it. I don't even need to run the code. I'm that confident this is correct. Returns can have ors, sure. Return is returning a bool, and or gives you a boolean. So if any of these 4 directions returns true, then we return true. Yes, there is a route in that direction. If all 4 of them return false, like if you go into a dead end, then it'll return false. There's not a route in that direction. And that's it. Okay. Is it simple? What is that, Bencourt? Okay. Yeah, let's find out if that actually works. I haven't had very much coffee today, so ignoring return value of int system. What is this doing? Oh, system clear. We don't need a system clear. We'll just see out clear screen that way. Okay. 1 1 2 2 3 3 4 4 1 0 0 5 5. Maze is not solvable. See, there is a bug. Okay. So now we need to debug it. All right. Oh, it's because we're starting on the location. So if the because we're marking the starting location as player, and so we start there. It's like nope, and it returns. So let's just not mark that spot. At the beginning. Let's see here. Let's just leave that spot open. And 1 1 2 2 3 3 4 4 0 0 and 5 5. Maze is solvable. Okay. 1 0 0 1 0 0 to 8 8. Maze is not solvable. There you go. What are you freaking out over, Aaron? All the rest of the code doesn't really matter. It's just the input handling, you know, like enter a wall, and if you choose your start location as a wall, then it will die, and it's the standard bookkeeping input stuff. I did have like a little animation before that I wanted to be a little fancy on it. And old man line 22. Yeah. So if you want to clear the screen, by the way, Control V, Control L. That's the clear screen character. That's the simplest way of clearing the screen. Just echo. There's a specific command code you can enter to clear the screen. Okay, so let's see, G++. So yeah, the first time I implemented this, I did a little illustration. It's showing you the BFS as it runs. It's kind of BFSing its way through, and you can see it dropping the crumbs as it goes along, and it's kind of floods outwards and stuff like that. But the actual, and then you can like move stuff like that. But the actual algorithm, just to see if there is a solution, is that. So then main.cc, that's it. For 6 lines of code. Would it have Stack Overflow issues? It could. What is your max stack size? What is your recursion depth versus the size of the maze? Sure. Good. So this won't work on a really large maze. And in cases like that, recursion is using the stack to keep track of where you are, right? And so you can always rewrite a recursive algorithm using literally a stack, like the standard library stack data structure. And you just push onto the stack, this is the current spot that I'm looking at. And so rather than doing this, what you do is you push north, south, east, and west. North, south, west, and east. Sorry. You push those tile locations onto the stack, and then you just constantly pop off the stack. When you pop off the stack, you check to see, is the spot the goal? If so, return true. Yay. If it's a wall, then you just delete it without processing it any further. And if it's an open spot, then you push its kids onto the stack as well. And so this whole thing can be done with just a little bit more effort by actually just creating a stack of locations, a stack of tiles, and you just push locations on it. So if you weren't able to do this assignment in the 2 hours that I gave you, it's fine. This is normally a week's assignment for like CSI 40, so it's not, don't beat yourselves up over this. Okay. Shouldn't you be able to bounce off the edges? Can you make this public for reference? Sure. So if you want to copy that is up in public maze.cc, and I will delete this in short order. So if you want to copy it by tomorrow, because this is actually a homework that I do give my CSI 40 students. So how is going out of bounds false? Well, let's say that we were like here, like on this spot here. Let me select, please. Select. There you go. Okay. So by the time we get to that spot, if we started down here, all the tiles down here have been marked with crumbs because we've been there before, and so we get to this spot here. And so every time we get to a spot, we just push the north, south, east, west. We don't check. I mean, we could check to see if the eastern tile is an open, and if it is, push it. We could do it that way, but instead what I do is I just blindly push north, south, east, west onto the stack, and then when we get to that spot, you have to see, was that spot that I pushed out of bounds? You could do the bounds checking before pushing those spots onto the stack. So you could say, all right, spot 1111 is out of bounds. So don't push them onto the stack. You could do it that way. But I just kind of like the look of this code because this kind of looks beautiful to me. You know, recursion oftentimes gives you these really neat looking, short, concise, beautiful looking codes. So all I'm going to do is return the OR of all four directions. So hunt to the north. It's like you're sending out a scout to the north, a scout to the south. You're sending out messengers in all directions, you know, looking for Princess Buttercup or something, you know. And so you just, and if that messenger comes back, yep, there's a route that way, you return, yep, there's a route from me, you know. But if all four of the messengers come back and say, nope, sorry, it's a dead end in all directions, then you say, okay, from this location, there is no route to the goal. And then you return that. Did you spend a lot of time drawing on the whiteboard to think of this solution? No, I just coded it for you right now. But I have the benefit of having TA'd this back when I did this. This was a week-long, you know, assignment we were given when I was in CSI 40, and when I TA'd CSI 40, I helped lots and lots of students figure out, and not every recursive solution is the same. Like I said, you can bounce check prior to going to the spot. You know, there's lots of different ways of doing it. So I TA'd that and helped walk students through it for years. And then I've given this assignment, like I said, in CSI 40 a number of times. So there's a lot of different ways you can do it. But we're doing recursion in this class, and so I thought it'd be fun to just do a little coding competition today and give you guys an opportunity to come up with a recursive solution to mazes. So. Sucks being a person who likes to use trial and error. I don't know. Like, yeah, trying code and seeing if it works is kind of like not exactly a good solution. It's better to write code that doesn't have bugs. You know. So it's like if you teach and TA this, you're already kind of used to the way to implement this. I guess. I mean, you know, the more times you solve a problem, you can just kind of like knock it out without burning too many brain cells, you know. But the reason why I did this is not to flex on you guys. It's to show you this approach to writing recursive code. The approach is you have your bounds, or not your bounds. You have your base condition, right? You have to have something that stops the recursion from running infinitely. And in this case, there's like 3, base conditions. There's 3 different ways it can stop. One is it's out of bounds. One is you're on a wall, or you find the goal, right? So technically there's like 5, you can go out of bounds 4 different ways. There's 3 different ways that spot could be taken. I could have, I kind of got rid of player, but so there's 2 ways the spot could be taken. Either it could be a wall, in which case, nope, no route's possible, it's a wall, so you return. Or a crumb means we've been here before. And this part here is actually the most important thing. You need to stop if it's been a place you've been to before. Otherwise, you will run in an infinite loop. And that's the number one problem most of my students would have when I TA'd this, was that they didn't understand you have to mark the spots somehow. There's a lot of different ways you can do this. But you have to mark the spot somehow, like I have been here before. You drop a little breadcrumb on the ground, and then if you ever come back, like you're recursing around, you come back to the same spot, then right, I've been here before, and then you return. If you don't mark it and you don't check it, then the code will infinitely loop, unless the maze has no loops in it. So if the maze has no loops in it, the code will appear to work. And that was something that got a lot of my students, because we would give them mazes that didn't have loops in them. And so they're like, my code works, what are you talking about? And then I'd delete one wall, so there would be a loop somewhere within the maze and their code would hang, So, can you explain the ORs and the return again? Yeah, so this is a recursive call, right? So if you tell me to solve the maze from row 0, column 0, which is what I used for my starting location, right? Then it's going to call itself. So none of these are true. So it marks row 0, column 0 with crumb, so we don't come back here again. And then it's going to call solve maze to the north. which is, and it pauses there. It calls solve maze to the north. That's out of bounds, right? Because I was at row 0 before, so this is row -1, so it's out of bounds. And so it immediately returns false. Okay, so that means there is not a route to the end zone. There's not a route to the goal to the north, because to the north is a wall, right? I drew a wall around the whole map to just kind of have a visual for me. Then we check to the south. Okay, and that is, if that's an open spot, it's going to start recursing. We're not going to come back to this location, to this version of solve maze, this level on the call stack for a long time, because if that spot's open, it's going to recurse. But let's say after like 50 chains of recursion down, it comes back true. There is a route to the end zone to the south. Then this whole thing will return true immediately, actually. It doesn't actually go west or east, because if a route was found to the south, because all of these are OR statements, right? If any of them is true, it's true. And so C++ has an optimization called short circuit optimization, so that if a route is found to the south, you don't have to recurse to the east and to the west, okay? Which could take a long time. It'll just immediately return true. And so our original function call of solve maze at row 0, column 0 returns true, because somewhere to the south there was a route found. And this seems like magic, right? It seems like magic. Because it's like, right, somewhere to the south. What? You know? But that's, when you're at the top level of the call chain, that's literally what it is. Return true if there is a route to the end zone if we went north. Return true if there's a route to the end zone if we went south from where we are, or west or east. Okay? And if none of those are true, if there is no routes to the end zone, if there's no routes to the end zone in either direction, north, south, east, or west, from the starting tile, then there's no route, and it returns false. Okay? And this is a recursive algorithm because it displays the self-similarity property, which means the subtask is the same as the supertask. So if you're trying to find a route halfway through the maze to the end zone, it's the exact same algorithm. Check to the north, check to the south, check to the east, check to the west. If any of those four directions, has a route to the end zone, there is a route to the end zone from me. And this self-similarity property works all the way down to the very base condition, where if we hit the goal, if is there a route to the end zone when you're standing on the end zone? Yes. Yes, there is a route to the end zone if you're standing on the end zone. You're in the end zone, so you return true. That's the base condition that makes everything work there. Okay? And then everything else returns false to make sure that you return false if there's not a route. And we do bounds checking, and if we're on a wall, there's no route. If we've been there before, there's no route, and we kind of got rid of that, so we could delete that if we wanted. What if you hit a dead end? Can you go back? If you hit a dead end, like let's say you're in a dead end, and you say return solve maze north, south, east, west. Comes the scout to the north comes back. Nope, it's a wall. Scout to the east. Nope, it's a wall. Scout to the south. Nope, it's a wall. Scout to the west. It's a crumb. Nope, it's a wall. It returns. And then it's going to rewind back up the call stack, and then you're now on the spot that was the crumb before. And it says, okay, to the east doesn't work. And then the other scouts come back. Nope, none of those are. Then it rewinds up the call stack. So it backtracks using the call stack, the function call stack, right? A function calls a function, calls a function, calls a function. And as those return, the call stack rewinds, and then they can go down and then rewind and things like that. How does this allow for maneuvering? Because it seems like we just take 4 routes, north, south, west, and east. What do you mean by maneuvering? There is no, we only can solve the maze in cardinal directions. If you wanted to allow diagonal movement, then we would add 4 more cases here. Northeast, northwest, southeast, and southwest. It would be a matter of just copying and pasting this and adding 4 more ors, you know. I feel like visualizing it would really help. Yeah, okay, let's. I mean, this is literally what it's doing. It's dropping breadcrumbs as it goes along. Okay, and so it recurses north, south, east, west. Oops, and north, south, east, west, north, south, east, west. This is doing BFS. This isn't the same algorithm that I just showed you right there, but it gives you the idea. So it recurses north, south, east, west, and then, yeah. Okay. So if you want to visualize the call stack, so let's say we got a maze. It's pretty simple. I'm just going to do a 3x3 maze. Wall, wall, start, end. Okay. So obviously there's a route like this, right? But you know, we need to find that. So when we start here, and we push onto the call stack this spot, this spot, this spot, and this spot. This one returns false. This one returns false. This one returns false. This one we don't know yet. So when we do this one, it pushes onto the call stack here, 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 and here. This one returns false, false, false. This one, don't know yet. And so if you were to visualize the call stack, you're going to have main, and then main calls into solve maze, which I'm going to abbreviate solve maze because I don't write the whole thing. And then that's solve maze at 0, 0. And then solve maze is going to call in the 4 directions. And the only one that doesn't return immediately is the one that's at row +1. So it calls solve maze with row 1, column 0. Then that one calls in the 4 directions. These 3 directions return immediately. I'm not going to draw them on the call stack. But essentially it's going to call solve maze with like -1 or you know, 1, -1. And that immediately returns because that's out of bounds, right? So so the only one that doesn't return immediately is this one, and that's at row 2, column 0. And then that one calls north, south, east, one. That has a crumb on it, right? So that immediately returns false. And then this is the only one that doesn't return immediately, so solve maze at row 2, column 1. And the call stack, you know, you just have a stack pointer, right? This is all done by the system for you. You don't have to maintain this call stack. You just call a function, and you're essentially using the system stack to track where you are and stuff like that. So then this one is going to call itself at SM22. False, false, false. False, falses, everywhere falses except for this one. So 22, and then that one is going to call solve maze at row 1, column 2, and that one's going to call solve maze on row 0, column 2. And then this guy returns true. Yay, it's true. And so when he returns the value to this guy says if either of the 4 directions, we're here now, we're talking about this one. We're talking about this guy right here. So if either of the 4 directions return true, this one returned false, east returned false, west returned false, south returned false. But because north returned true, I return true. And so it returns a true back up to this one. So true gets passed back up, back up, back up, back up, back up, and then solve maze returns true back to main. Because either of the 4 directions return true. So it returns true back to main, and main says, yes, the maze is solvable. If, however, there was a wall here or something, if that was a wall, then this one would return false. And since all 4 directions were false, it returns false. Because all 4 directions were false, it returns false. And all of them would be false coming back up, and then main would get a false instead of a true. And it would print the maze is not solvable. Okay. So that's what's going on underneath the hood. If you were to look at the call stack. So you can actually print out the call stack. See, how can we crash this? Let's crash the code. I'm just not good at crashing code. Give me a second. So if we find the goal, yeah, let's crash it if we find the goal. So if we find the goal, then return 1 divided by 0. Let's try that. Warning you, I know. Input file 1, floating point exception. Okay, so it crashes when we hit the goal. Okay, so GDB, okay, so let's compile the code with debugging turned on, main.cc, so -g turns on debugging. And so what we're going to do is we're going to run this code inside of the debugger. So GDB a.out runs your program inside of a debugger. And so GDB now runs, it runs your program, it loads your program, you hit run, and then it's going to, this is inside of the debugger, by the way. Okay. 1, and starting location of 0, 0, goal location of 9, 9, then it crashes. So it's running, it crashes. And so the GDB says program received signal SIG floating point exception, FPE floating point exception, arithmetic exception. Just use a single equal sign. Yeah, Yoxtimer. Okay. Some of you are pretty good at crashing code. Yeah. If you have any ideas, let me know. So, so GDB tells us it crashed inside of a function called solve maze. The value of row was 9. The value of column was 9. So we crashed on the goal. It's telling us this. Main.cc line 24. This is the line of code we crashed on. If spot equals goal, return 1 over row. And we can type backtrace. If we backtrace, you can see the call stack. Okay? This is why I wanted to do this, because it'll visualize the call stack for you. And so you can see that we are, hit enter for more. So main called solve maze, which called solve maze, which called solve maze, which called solve maze, which all the way down. So we are 85 function calls deep right now. So yeah, it's at the very bottom of the call stack. So this function on line 28 called us. This function on line 28 called us. And so you can actually see that you can trace your entire flow of execution, starting at row 0, column 0, all the way down to row 9, column 9. Oops. You can see how it got called. Okay. Can't you also type to see where it broke? Yeah, it broke right here, line 24. And it prints the line. And if you want to see values, you could like print row. Row is 9. Print column is 9. GDB has tons of options, but basically everything you need to know for at least something like this, it just tells you everything you need to know here. And if you type backtrace or BT for short, then you can look at the. This is very useful for recursive algorithms, by the way, because if you Stack Overflow, like let's say we take out. Yeah. Okay. Here's an even better one. Yeah. Let's kill it. So let's take out that crash. So let's just take out the check for crumbs, right? So let's just take out the check for crumbs and only check for mazes. Oops. G++ main.cc. Starting location 0, 0, ending location 9, 9. Segfault. Why did it segfault? I took out this one little thing here. I took out this one little check to see if the spot is a crumb. Why did it segfault? How did I get a segmentation violation? Wish we could have a GDB class. I do give GDB classes occasionally. Yeah. Why? Why am I segfaulting? Sure, you do a class on GDB. It's fine. I just gave you a class on GDB, by the way. That's really all you need to know for most of the stuff. There's tons and tons of options, but what I just showed you is actually the most important part. So why did it segfault? Yeah, infinite loop. It goes east, it goes west. It goes east, it goes west. It goes east, it goes west. I'm not, even though I'm marking it down as having a crumb, I'm not actually stopping myself if I'm on a crumb. So it just infinite loops. Okay, so we can detect this by compiling the code. Here you go. You guys want a GDB workshop? Here you go. Compile your code with -G, and I think it probably does that for you by default. Yeah, if you type alias G++, you can see it should have -G on by default. If not, I'll just give you the instructions anyway. Okay, step 1, compile the code with debugging turned on. Step 2, run GDB a.out. So GDB is the GNU debugger, written by my boy Richard Stallman, or at least originally by him. And then you pass the executable, and that will load the executable inside the debugger. And now you're at the GDB console. The GDB console has ridiculous amounts of options. Help all. These are all the different commands in GDB. There's a lot. There's a lot of them. So the most important one would be run. So run begins running the program, or you can step. You set a breakpoint. Break on line 22 or something. Okay, so we can run, and then we'll just pass in no 0099. Okay, so then if you hit a breakpoint, I said break on line 22, then it will run until it hits the breakpoint. Okay, and then you can hit run again. Step, and then you can actually step through your program like this. And at any point, you can print values of things. Like you can print the value of row, you can print the value of column, right? And so the first time we call this function, row is 0, column is 0. Okay. So that's you can literally step through your thing. You can set up a TUI where the variables are up top, and you can see everything kind of visually. But I usually don't run it that way. I like when I was in college, I would step through my program and visualize every line as it's running and print the values and make sure it's doing exactly what I wanted. And then I realized I didn't really need to go to all that rigmarole. I can just run it till it crashes. 00 to 99, segfault. You just run it till it crashes, and then you can just backtrace it. And the backtrace holds all of the information on every variable. I could go up the call stack and be like, what are the variables in function call number 10, and it'll print it out for me. So I actually don't need to step through the execution. I can just let it die and then see why it died, and that's usually all I really need to figure out what's going on here. So you can see how many times the function has called itself, and it just keeps calling itself in an infinite loop. You see this? It goes from 00 to 10, so it goes south, and then it goes back north, then it goes south, then it goes back north, then it goes south, then it goes back north, over and over and over again infinitely, which is the bug, right? To continue without paging. Bloop. So you can see how many times it called itself before it segfaulted. It segfaulted pretty fast, too. And you can see the call depth is actually pretty deep on this before it crashed, because there's not really... we're not using too much stack space every call, so it actually could go for quite a while before it crashes. So you can see this is what happened in that split second before it segfaulted. Yeah, this is backtrace. Yeah, so you basically okay. Enough. So that's it. That's all you really need to know. Okay. So Vim GDB notes. Step 1, C++, your code with -G. Step 2, GDB get it out. Step 3, run. Let it crash. If your code's not running properly, then you can set a breakpoint or something. But if your code's running and just not working properly, I tend to just see out the values because it's faster than doing this. Run, let it crash, and then backtrace. Or BT. Print X prints value of X. That's it. That's all you really need to know to do GDB. Okay. Okay. Might help you with your merge sort algorithm. You can also set a breakpoint and let it run until the breakpoint. Then step to move to the code one line at a time. You can step into a function. You can step over a function. Just lots and lots and lots of options for GDB. Isn't Stallman the guy with the laptop? Yeah. He spent the night at my house a few years ago. Weird dude. He's a super weird dude. I like him a lot, though. So, he's one of the world's greatest Uber nerds. He's as famous as like Bill Gates or Steve Jobs, who wasn't really a nerd. You know, Steve Jobs is a marketing guy. Steve Wozniak in nerd circles is more respected than Steve Jobs. You know. Bill Gates at least was a techie, you know, like Bill Gates actually knew his tech. Steve Jobs is a marketing guy. Unix kernel, no, that's Linus Torvalds. Linus Torvalds is another one of those uber geeks, you know. There's also Eric S. Raymond, who started the Open Source Institute, and Richard Stallman started the Free Software Foundation, which you can see I have a sticker for right there. Given to me by Stallman himself. He handed that to me for letting me stay at his house, or letting him stay at my house, rather. So that was a present from him. Right there, that kind of oval one right there. Then I got an EFF sticker right there. It's from the Electronic Freedom Foundation. China Peak, REI, I don't know. For years, I collected bumper stickers and never did anything with them, but then I started streaming live, so I'm like, alright, I'll just use my stickers and just put something right behind my head. So that's what's going on there. I think one of my daughter's campaign stickers, Gibraltar Hardware, Thrones. Dennis Ritchie, yeah, he's another big Uber nerd that's dead now. Yeah. Ken Thompson. Yeah, there's a lot of people that... yeah, there you go. Dennis Ritchie right there. Bjarne Strustrup, of course. So Min Curley was asking about a good reference manual for C++. The Mountain book is pretty good. It's a modern C++, so it's a little bit out of date, but there hasn't been too much added to C++ since C++ 11. That was the last like really major revision. So like if you want to know what is the maximum float, what is the maximum double, what is the maximum int, there is limits. You can include limits, and then that'll tell you the maximum and minimum values for all those different things. So there's a lot of good references. If you want to learn about Unix, this is a really old book, the Sobel book, but this is, I got a used copy for like $5 or something. And this is actually the book that I got in college that I learned Unix from. So this is a really good book on learning Unix. What I would do is I would just flip it open to a random page, like that. And it's like, okay, oh, here's a chapter on make. Kind of useful. Kind of comes up. Source code management. This doesn't have Git in it because it way predates Git, but the principles of source code management, kind of important. How to copy a file. So basically what I do is every day I would just open it to a random chapter and Learned about RCP, how to do a remote copy. And over time, I just kind of learned all the commands. Make a directory. Make a directory. More, how to show one page of text at a time. So, it's a really good book, and you know, all those commands are still in the Linux kernel. It's outdated, but it's not outdated. Those are still the basic commands that we use all the time in Unix. Jason Gregory's Game Engine Architecture. Let's take a look. And we're out of time. If you guys need to peace out, it's fine too. Let's see this Game Engine Architecture by Gregory. Let's see. All right, yeah, I'll pick this one up. I have a couple game engine books. Let's see if I can find them. Helps in starting to use GitHub. Yeah, how do I just show my Kindle books? It's in there somewhere. Wonderful shelf here. Orders from 2021. Game. Yeah, this one. Okay, so this is a pretty good book too. So this is by a professor at USC. USC has a pretty decent game development program there. You can major in game development, and so this is a pretty comprehensive, you know, guide to making game engines and games in C++. So they use the SDL for the API for it. And you bought this one? Yeah. So, yeah, this is a good book. This is a good book. And there was one other I got recently, which wasn't on Amazon, so I can't look it up. But it goes over game engine architecture and stuff as well. I don't remember the name of it off the top of my head. Okay. So that's it for today, guys. Hopefully this was useful for you. I can throw up the notes here on GDB, and I'll pin this for you. So it should help you as you do merge sort, maybe. If your merge sort runs forever and crashes, then do this, and you can fix the bug. So don't leave my code in a bad state. Okay. Yep, trying and failing is one of the best ways of learning. Okay. Yep. So thanks a lot, everyone. And I will see you guys on Tuesday. Get your merge sort golf done by then. If you have any questions, post on Help Center. Okay. Peace out.